first transaction log from our previous slide. There is one active virtual log file with the status of 2. So in this scenario where we had a SQL server with, we'll say, 10 different transaction logs at 1 gig each, if the records we need to acquire are within the active VLF, we could acquire just that one transaction log as opposed to the other 9 gigs worth of transaction space. So again, just ways on how to reduce the scope of the evidence you acquire. So once we know where the transaction logs are stored, what the VLF status of these transaction logs are, we can actually obtain or extract the records that are loaded within the actual transaction log. FinDBlog is a function that's new within SQL Server 2005, and it's extremely flexible, and you can execute fantastic queries against this. What you can do is, depending on your investigation, if the investigation is around a given object, again, I'll go back to the scenario, someone modified the HR database table, you can look at a transaction log file that's, we'll just say 10 gig, and tell it, just give me all the transactions that modified this HR database table, and it will dump just those transactions for you. Or you can tell it, just dump specific columns. Based on earlier in the presentation, there's over 100 columns. If we're going to focus on 8, we can dump just those 8 columns. And as well, you can focus on just a SPID. If that SPID is tied to a user in question, you can dump all the transactions that that user actually executed within the database, or all transactions within a given date or time range. So it's extremely flexible, and it's brand new within SQL Server 2005. DBCC log has been with SQL Server since SQL Server 6.5. It's more resource intensive. It dumps the transaction log in its entirety, so there's not a lot of flexibility in terms of filtering records. What it does come with, though, is some default filters, which you can specify minimal information, slightly more information, full information, detailed information. Based on my experience, option 3 is the best for DBCC log, just based on the level of detail it gives you, the output, and as well, it gives you the hexadecimal dumps as well, so that's pretty, it's pretty handy. Moving along with evidence collection, collecting the database plan cache. The following query, select star from sysdm x cached plans and cross-applying the SQL text plan. What this does is it dumps all of the execution plans within the SQL Server plan cache. And what the second part of that query does is it dumps the actual text that was executed that created that plan. So you can look at a hash bucket or a SQL Server plan execution, and you can look at the actual statement that was executed in plain text in English against the SQL Server. So it's highly recommended to include the SQL text within that statement. In addition to the plan cache, the default statement up above, the additional plan cache specifics, the below 2 queries, the select star from sysdm execute query stats, and the other one executing against the plan attributes, allow you to dump additional details, including the user who belongs to the schema who executed that query, the date the query was executed, the last time the plan was used. These are all facts that you can extract as well based on plan cache entries by executing those additional 2 queries. Collecting database data files and log files, by default they're stored in the MSQL data directory under the .mdf or LDF extensions. Self-explanatory how to acquire those. You can use your DD, DCF, LDD, any tool of your choice. Same goes with the default trace files. They're located within the MSQL log directory. And these trace files carry the name log underscore, then it'll be a number, .trc. Every time the SQL Server service is restarted, the number is incremented by 1. So if we have a log underscore 1.trc, we restart that SQL Server service. A new log file, log underscore 2.trc, will be created. So you're going to have a history of all the default trace entries that have occurred within that SQL Server. In addition, SQL Server error logs also within the /log directory. The name of this file is just named error log. When the error log is full or the SQL Server service is restarted, the existing error log is renamed to errorlog.1 and a new error log is created. And it maintains a history of up to 7 error logs. So you're going to want to require all error logs, assuming that's within the scope of your investigation. Collecting system event logs, that's self-explanatory. You can collect the EVT files, or WFT automates that for you if you decide to run that earlier in the investigation. Now that we've gone over how to collect evidence, a primer of evidence, now we're going to go into how to actually analyze it. We get into the good stuff now. Windows event log, touched on this briefly before, but what it records are authentication data, so failures, successful logins, log-offs, SQL Server startup and shutdown activity, and as well the IP address of SQL Server client connections. With SQL Server, there are many protocols, many ways to connect to a SQL Server. You have TCP/IP, you have shared memory, and you have name pipes. With SQL Server logging, TCP/IP, it will record the actual IP address within the Windows event log. Shared memory, it's interactive, so you have to look at who is logged into the actual database server. But name pipes does not record the IP address of the machine that is connecting to SQL Server. However, if you do run Windows Forensic Tool Chest, it does dump all the connections and sessions within the Windows level, and you can map that back to figure out who was writing that name pipe and connected to that SQL Server. The error log records the exact same information as the Windows event log, the authentication data, startup and shutdown, and the IP address of TCP/IP connections. The advantage of 2 different log sources are they have different retention periods. Again, error log when you restart it, and Windows event log, it's based on how you customize it by size, by date, etc. But you can compare log file against log file. In some cases, a log file might become corrupt or might be tampered with. So it's good to have 2 different sources of the information when conducting an investigation. The default database trace, again, it includes authentication history, but in addition, it actually records DDL operations. So if someone creates a table, that's going to be logged within your default trace. If someone creates a user or grants privileges to that user, that is recorded in the DDL trace as well. And IP addresses of SQL Server client connections, again, is recorded. The application that was used to connect to the SQL Server, to the best of Microsoft's ability, is recorded within this as well. So based on the example we have here, under the application name column, we have OSQL32, which is the name of the application that was used to actually connect to SQL Server. One of the most important elements of this default database trace is it maps a SPID, which again is how SQL Server distinguishes who's doing what within the database. It maps that to an actual login name. So that's extremely beneficial to put a name to SPID 51, 52, 53, etc. Data files and log files for evidence analysis. What you should do is just attach the data files, self-explanatory, and these are going to be used to obtain on-demand schema information, data page contents, etc. And the very next slide, throughout the rest of the presentation, we're going to take a deep look into the actual data files that we're attaching. And the active transaction log imported into Excel or Access for viewing. Excel has limitation, I think 65,000 rows, so you might want to use Access or some other database to look at the actual transaction log files. Once they're dumped, you want to identify the DML and DDL statements, in addition to map the transactions to a given SPID. So now we get to the nuts and bolts of what's going on within the transaction log. I'm looking at an update operation. The transaction log contains multiple columns. Operation is exactly what type of transaction was executed within a database server. The begin transaction and commit transaction note the beginning and the end of an actual transaction. In the middle contains exactly what type of transaction it was. So a modified columns equals an update by SQL Server. Transaction ID is an identifier used by SQL Server just to group like transactions together. Page ID, and transaction ID is a hexadecimal representation of the transaction ID. Page ID, what that does is it references the actual data page that was modified by that transaction. Again, that's a hexadecimal representation of a decimal page identifier. Slot ID is the actual row within the data page that has been modified. Offset and row is the area within the row that was actually modified. So in most cases, offset and row would tell you exactly what column within a table, within a data page was modified. So putting it all together, looking at this slide, we have one transaction that modified 3 records on 3 different database pages, 3 different rows on 3 different database pages, but the same column was updated within this transaction. So that's at a high level, putting it together, and we're going to take it to the next level on the very next slide. DBCC page will dump the actual contents of a data page that was modified. So based on the previous slide, the page ID of the first transaction was 211. So if we add that as an argument to our DBCC page, what that will do is that will dump the data page, and below the actual page header will give us the object ID. That object ID is the owning object of the data page. Just because we know the data page, we have no idea what object that data page belongs to. Looking at the header will give us the actual object ID. We throw that object ID into a statement, simple select star from sysobjects, and that will tell us the actual object that was modified. So if we look at the results, the order table, x type equals user table, so the order table was modified as part of that transaction. Now that we know what was modified, we need to know exactly what was done to it. And before we do that, we're going to need to figure out exactly what the schema is. So in order to get the schema of the order table, we can dump the following query, select call order, name, data type, etc. from syscolumns, where the object ID equals the object ID that we gathered from the transaction log. What this does is it dumps the order ID of the columns within the actual database. It's extremely important that we understand the order of columns within the database. When you create a table, the order you specify, the different columns within the table, dictate how SQL Server will actually write data to that table. So once in the upcoming slides, we're going to look at a lot of data elements that are written to the table. The order that the data elements are written are denoted here within the call order. If you look at credit card number, which is call order 9, and ship status ID, which is call order 11, 10 is missing. If any modifications are made to the database table, meaning if someone drops a column, it just removes that line from the results. So the order is still correct, but you might come into account, hey, I'm missing a 10, I'm missing a 9. What happened here? It just means someone performed a schema update and removed the column after the table was originally defined. And in addition to the order, we can gather the list of the data types that were in use. Again, SQL Server stores data differently, retrieves data differently, depending on the data type in use, and the length. By looking at the results here, we see some varchar, which are variable length, and we see some integer and date time, which are fixed length. So SQL Server takes the high water mark, and even though it includes fixed and variable length columns, it will store that column as a variable length row. So again, looking at the